that is a layman answer. But where here we want that there should be a technical definition for this. So the technical definition for the stability I am writing here, that for stability is that for bounded input there should be a bounded output. Okay, that should be clear. Bounded input means which is within the BI. I am simply writing BI, bounded input. Okay, bounded input means within the limits. Okay, that is the things if are within the limits, that is they are not growing exponentially or not growing at accelerating rate with time. Okay, so if they are within limits, we say, for example, your square waveform. If I write down the square waveform, okay, its input is constant. Suppose A is value, and it is for 0 to 1 second, then from 1 to 2 seconds it is negative value, so it is within the limits. Okay, now suppose I give you an input like this, so it is unboundedly increasing, okay. So the definitely if something is already in unbounded in nature, its output probably is generally unbounded also. So so when we are giving a wrong input, we will definitely get a wrong output. So we are not concerned with unbounded output, but if we are providing a bounded input, okay, and we are getting a bounded output, again bounded output means within the limits, then we say system is stable. So the stability definition from input and output relationship, that if a bounded input is given to the system and the system is giving an bounded output, we say system is stable. Now there can be one case you are giving a bounded input and the system is unbounded output. Okay, that is the output is increasing. Again, the system is, we will call this system as an unstable. So dear students, please keep in mind that there are two definitions are there. Okay, for stability, bounded input, we should get bounded output, and for instability and unstable system, or people may call it instability. Okay, the another word for unstable is instability. For instability, if you are applying a bounded input and you are getting unbounded output, then you call that system to be an unstable. Okay, so this is what the scientific definition for the stability. Okay, now, so what happens? If I ask now you that, sir, determine the stability of any system, any control system which is being given to you, because you are being controlling the system only purpose is to make the system stable. You are getting the output, but the output is not stable. Okay, no one is going to purchase that product, no one is going to process that product or the plant. Okay, so stability is the main criteria, and in our control system mainly revolves around the stability also. And any new things which you design, any new product you design, any new process you define, the most important thing is seen, that is stability. Therefore, there should be some methods to determine the stability methods, to determine the stability of the system. And one such method is Routh Hurwitz stability criteria. This is a very important, and every year there are questions are being asked related to it. So let us talk about, so what is the Routh Hurwitz stability criteria? It is a method for determining continuous system stability. Okay, and it is stated that, and what is stated that it is a mathematical method. Okay, it is a mathematical method which states that the number of roots of the characteristic equation with positive real parts, roots of characteristic with positive real part is equal to number of changes in the sign of the first column of Routh array. So what happens? We have to frame Routh array. Okay, the basic important point here is the Routh array. So we will create a Routh array. Okay, and we will see the number of the sign changes in the first column of the Routh array. If the number of sign changes are there, then the number of sign changes equal to the number of roots of the characteristic equation with positive real parts. Now, positive real parts means, definitely you will ask, positive real parts. Positive real parts simply means that the roots are lying in the right hand of the S-plane. So let me clear one more important point here, that what is this right hand and left hand of S-plane? Now you know that our roots What are roots? The roots of the characteristic equations. Okay. When the denominator is equal to 0, then the denominator of a transfer function is made equal to 0. Now you have a transfer function. Okay. How it is defined? Okay, it is defined as numerator. There is some numerator expression and there is a denominator expression ds. Ns over ds. Okay, which is also equal to cs by rs. Now, if I make ds is equal to 0, what happens? This equation is called characteristic equation. This equation is called characteristic equation. And in terms of closed loop transfer function, if you remember, what is closed loop transfer function? Gs upon 1 plus GS. GS is the forward transfer function and HS is the feedback transfer function. Sorry. Okay, so if I equate 1 plus GS HS equal to 0, okay, then the equation to obtain is called characteristic equation, and the roots are nothing but the poles of the system. The roots are nothing but the poles of the system. Now, and if I make GS is equal to 0, then the roots obtained are called zeros of the system. And I used to plot these poles and zeros on these poles are represented by cross and the zeros are represented by a small circle. So these poles and zeros are plotted on a plane called S plane. So this plane, now this S plane, as I've already told you, have two axes. One is called the real axis. Okay, the x-axis is called the real axis, positive real axis, and this is minus negative real axis. Okay, and the vertical line is called the imaginary axis. So it has also two parts, the positive imaginary axis plus j omega axis, and this is minus j omega axis. So remember, the poles and zeros are plotted on S plane, which has the two axes. The real axis is called, the x-axis is called the real axis, and while the y-axis is called the imaginary axis, plus j omega on the upward side and minus j omega on the downward side. Similarly, on the right hand side of the x-axis, we have a plus real axis, and on the left hand side of the real axis, on the left hand side we have a negative real axis. Okay, and poles and zeros are plotted on these S plane only. Now one condition is that the pole should lie on the left hand half of the S plane in order to system to be stable. So keep in mind that in order to be system to be stable, the pole should lie on the left hand half of the S plane. So definitely you say, sir, why we are going for Routh Hurwitz criteria? Okay, we should solve the equation. That is the characteristic equation. Determine the poles. Okay, if we see that the poles are lying on the left hand half of the S plane, all the poles are lying on the left hand half of the S plane, system is stable. And if we see that no, they are lying on the right hand half of the S plane, we will say yes, system is unstable. If any of the pole is lying on the right hand half of the S plane, the system is unstable. Mind it, if any of the pole is lying on the right hand half of the S plane, system is unstable. Suppose there are 4 poles are there. Out of the 4 poles, 3 are lying on here. 3 are lying on the left hand half of the S plane like this. Okay, and one of them is lying on the left hand half, on the right hand half of the S plane. Sorry, then system is unstable. So what conclusion I am getting, that if any one of the pole is lying on the right hand half of the S plane, system is unstable. Okay, so that should be clear. Now you will analyze, sir, why we are going for Routh Hurwitz criteria when we have to solve the equation only. But mind it, you will be feeling uncomfortable while solving any equation with order greater than 3 or 3 or greater than 3. Up to 2, if the equation degree is 2, highest degree is 2, that is very simple. It is a quadratic equation and you can solve by the formula minus b plus minus under root b square minus 4ac upon 2a. But suppose if the order is 3 and they cannot be factorized, that is very difficult to find out the roots. And if it increases, if the order of the system is 4, that is the degree of the characteristic equation is 4, degree is 5, degree is 6, degree is 7, then it is very difficult to solve such equation, and for that purpose we will go for Routh Hurwitz criteria. So up to 2 the things are very easy. If the degree of the equation is 2, the things are very easy. But if the degree is greater than 2, 3, 4, 5, 6, then we have to go for Routh Hurwitz stability criteria. So, and what does this stability criteria state? That, let me clear, it states that the number of the roots of the characteristic equation with positive real parts is equal to the number of changes in the sign of the first column of the Routh array. So before understanding this statement, let us form the Routh array. Okay, so this method will yield stability information without to need to solve for the closed loop system pole. So you did not have to solve the equation. Okay, you apply this method and you will come to know about the stability and instability of the system. So we can tell how many closed loop system poles are in the left hand of the S plane and how many are in the right hand of the S plane and on the j omega axis. But we cannot, but important point, notice we say that how many but not where. It means you does not know the location of the poles, but you know that these poles, that out of 5 poles, 4 are locating on the left hand of the S plane and 1 is locating on the right hand of the S plane. But where they are being located, where is the exact position, that we don't know through this Routh Hurwitz stability criteria. So this is one of the drawback of the Routh Hurwitz stability criteria. So there are other methods also there which are improving this. So but before this, proceeding to the other methods, we let us focus on this method. So what this method required? This method required generate a data table which is called a Routh table and interrupt the Routh table to tell how many closed loop poles are there in the left hand of the S plane, the right hand of the S plane and on the j omega axis. So how to do it? Let us see. Let us take an example. Okay, in this example, you know, transfer function is being given. CS by RS is nothing but NS over A4 S raised to the power 4 plus A3 S raised to the power 3 plus A2 S square plus A1S plus A naught. So the denominator portion, mind it, this is the, we have to take into account the denominator and equate it to 0, then it will become our characteristic equation. So the characteristic equation of the given system is nothing but A4 S raised to the power 4, A3 S raised to the power 3, A2 S raised to the power 2 plus A1S plus A naught. So this is the, when equated to 0, this became a characteristic equation. So we have to take into account the characteristic equation in order to form the Routh array. So how to form that Routh array? Let us. So it is clear. So what is the highest order? S4. So the first column we will starting from the highest order, highest degree, S raised to the power 4. Then I will write S cube. Second row, third row S square, fourth row S raised to the power 1, and I will continue up to S raised to the power 0. So I will write down in the sequence. And now in the very first row, what I will write down the alternative coefficients starting from the highest degree. So highest degree coefficient S raised to the power A4 and then alternative. I will skip A3 and I will write A2. Then I will skip A1 and write A0. Okay. And the remaining skipping things are being kept in the, will be written in the second row. So A3, then A1, and that should be in an order. It should not that you will first order A1 and then A3. No, you have skipped first one A3, so you write A3 here, A1 here, and nothing else. So it is 0. Now with the help of these two arrows, these two rows, so the first two rows of the arrays are obtained from the characteristic equation only. So first you have to obtain the characteristic equation of the system, or it will be given directly. Sometimes in the question directly the characteristic equations are being given. Okay. Now what will happen? Now you will do mathematics for the remaining rows. So after S cube row, the remaining row is S2. The next row is S2. So what will be the coefficient of the S2? So how will you find out? What you will do? You will form a small matrix, an array. And what is the value of that array? A cross multiply. A4 multiply by A1. Okay, like this. A4, A2, A3, A1 with minus sign. Mind it. So A4 multiply by A1 minus A3. So it will be definitely, it will be a minus sign. You did not have to worry. Basically, it is A4 multiply by A1 minus A3 by A2 divided by this coefficient A3, the first coefficient. The first coefficient associated with the just above the row A3, and that will be equal to B1. Similarly, here also, what you will take the first row, the first column, and the coefficient of the third. So A4 multiply by 0 minus A3 multiply by A0 divided by this first coefficient A3, that will be your B2. Similarly here nothing will be there because we are not, so it will be 0. Now let us come by S1. For S1 we will take into account this one. So 1 minute, huh? Wait for a minute. A1 multiply by A1. Yeah. Now, in order to calculate the coefficient for S1, what you will do? You will take these two rows. You will take these two rows. Okay. So A3 multiply by B2 minus B1 multiply by A1 divided by B1, that will become a C1. Similarly, for finding out the coefficient for this, let's say it is C2. Therefore, it will be what happens? You have to take A3 multiply by, yes, A3 multiply by A3 multiply by 0 and B1 multiply by 0 and divided by this coefficient B1, that will be 0, and similarly you can find for the third row. Now for finding out the coefficient for S0, the elements in the S0 row, so what you will do? You will take these two rows. So first of all, B1 multiply by 0 minus C1 multiply by B2, okay, divided by C1, so this will become D1. Similarly, B1 multiply by 0, C1 multiply by 0 divided by B1 will be the this second element, and definitely nothing is being left, though this will be a 0 element. In this way, the Routh table is being prepared. Okay. So now we will take 4 cases. Now what will happens? Once you have formed this Routh table, what you will see? You will check this first column, as I've already told you in my definition. Okay, that using this we can this is the definition. Okay, the number of the roots of the quadratic equation with positive real part is equal to number of changes in the sign of the first column of the Routh array. Okay, so this is A4, this is positive, A3 is positive, B1 is positive, C1 is positive, D1 is positive. So all roots are positive in the first column, then we say the system is stable. Now had there been a minus sign here. Now let us take the case. Had there been minus sign, then this is positive, but this became negative. So from positive to negative, one change. From negative to again this is positive, 2 changes. So 2 changes of 2 sign changes are there. So what we say that the 2 roots are lying on the right hand of the S plane, hence the system is stable. So whenever there is sign change is there in the first column of the Routh array, then we say the system is unstable. Okay, if all the signs are positive, then we say system is stable. So now we'll take some special cases. No element in the first column is 0. Case second, a 0 in the first column, but some other elements of the row containing the 0 in the first column are non-zero. Case third, entire row is 0. So we will take all these 3 cases. No element in the first column is 0. Okay, so let us take the first. A very simple equation has been given. S cube plus 6x square plus 12s plus 8. So I will form a Routh array. So first of all, I will what I will do? I will write down s cube, highest degree is 3, s square, s1, s raised to the power 0. Okay. Now I will write down the coefficient, alternative coefficient. The first coefficient is 1. Skip this. Second is 12. And nothing is there, therefore 0. Because I will skip, then nothing 0. Now I will write down the skipping element in the order, the sequential order. First will come 6, like this. Second will come 8 and 0. Now I will find out the remaining. So how will you find out the remaining? Okay. So what I will do? 12 6 12 6 72. 72 minus 8. 64 divided by this element 6. So 64 by 6. This element 6 multiplied by 0 minus 1 upon 0. So 6 multiplied by 0 minus 1 over 0. So 0 by 6 is 0, nothing. Okay. And because no element exists, so there will be no other element. Now we find out with this 64 by 6 multiplied by 8. Okay. Minus 6 by 0 upon 64 by 6. So it will come out to be 8. So, and for the remaining, nothing is there. Therefore, nothing element is. Now see, what is the sign? How many sign changes are there in the first column? This is positive. 1 is positive. 6 is positive. 64 by 6 is positive. And 8 is positive. Hence, all signs are positive. There is no sign changes there. Hence, the system is stable. So you will write the system is stable for this particular system. So very clear, very simple example. This is the case first, a normal case. Okay. Now let us take the second case. I have already told you no sign changes there. Hence system is stable. Now let us take the this given below. So again we will form a Routh array. S cube, s square, s1, s raised to the power. What are the power? 1, 2 in the first row, 1 and 24 in the second row. Very clear. Okay. Now I will multiply it. So 1 multiplied by 2, 2 minus 24 is minus 22 divided by minus 20. This is 0. Then this is multiplied by, I will get 24. So I will form the Routh array. Now see, plus is there here. This is plus. This is plus. Oh, this is minus. So one sign change is there. Now from minus to here also what? Plus. So two sign changes are there. So it is, first of all, sign change is indicating the system is unstable. Okay. And also, since two sign changes are there, therefore it clearly indicates that two poles are lying in the right hand half of the S plane. Okay. So two sign change in the appear in the first column. We find that two roots of the quadratic equation lie in the right hand half of the S plane. Hence the system is unstable. Mind it, we have only find out how many, but at what location we don't know. We don't know. So this is the drawback of the Routh Hurwitz criteria. We will come to know whether the system is stable or unstable. Okay, but we don't know what are its roots. So let us take another example. Okay, determine the value of the K for which system is stable. So this type of question we generally use Routh Hurwitz criteria. What should be the value of K for system to be stable? So first of all, we will form the Routh array. Let us form the Routh array. So s cube, s square, s1, s raised to the power 0 is there. 1, 3, 0. Then the remaining skipping element 3, 1 plus k and 0. So now we will find out 3 multiplied by 3, 9, 9 minus 1 minus k, 8 minus k by 3, 0, 1 plus k. Now in order that system should be stable, this is positive, 8 minus k upon 3 should also be positive. 8 minus k upon 3 should be positive, and positive means should be greater than 0. Okay, and also 1 plus k should also be greater than 0. Now you solve these two inequalities. Okay, you will get the value of the limitly value of the k. Okay, so when you will solve it, what you will get, 8 is greater than k. 8 is greater than k, or k is less than 8. So the value of k should be less, and when you solve this, k should be greater than minus 1. Okay, so what we will get that k should lie between -1 to a. So this is the solution in order that system to be stable. So sorry for the inconvenience. So what we have found from this, that from solving these two inequality, that the value of the k should lies between -1 and 8, -1 and 8. So this type of questions are also being asked in the examination, where we have to determine the value of this k in order to the system to be stable. So if the k is 9, then system will become unstable. Okay, if k is 7, then it is definitely a stable. So the value of the gain is much very reflected in determining the stability of the system, that you have to keep in the mind. So let's take another. Find the stability of the system shown below using Routh criteria. So this type of question can be also be there. So first of all, look towards the question. There is GS is being given and there is a HS is there. Now mind it, HS is a unity feedback system here. HS is your 1 and this is your GS. Okay, so first of all, find out the characteristic equation. So what you will do, what is characteristic equation for a closed loop transfer function? Negative feedback 1 plus GS HS is equal to 0. So find out the characteristic equation. So 1 is already there, GS is 100 upon S plus 2, S plus 3, S plus 5 and HS is 1. You solve it, okay, and equate it to 0, you will get the characteristic equation. So let us find out what is the characteristic equation. So closed loop transfer function is this much, okay. So the characteristic equations comes out to be S cube plus 10s square plus 31s plus 1030. Okay, so with this background, let us form the Routh array. So the first coefficient is 1, skipping the second and come to third 31 and then 0. Then write down the skipping element 10 and 1030. So for your convenience, you can solve also if in a particular row. So for example, you can, because 1030 will be very large quantity, or you can solve if you have a calculator, you can solve also. So I am cancelling out 10 1 10 and 10 times 103. So this can be also one solution. Now I find the Routh array criteria. I will apply the form the Routh array. So it will minus 72, 0 and 0. How minus 72 has come? 1 multiplied by 31 minus 1 multiplied by 103 divided by 1. So minus 72. Similarly, 1 multiplied by 0, okay, and 1 minus 1 multiplied by 0 divided by 1, 0, 0. So 103 and like this. So what conclusion you are getting? That this is the Routh array you have formed, looks toward the first column. This is positive, but this is negative. So positive to negative, one sign change. Then again from negative to positive, again two sign changes. So it is clearly indicated that there are two sign changes are there. Therefore, system is unstable, and also the two roots of this two poles of this system are lying on the right hand half of the S plane. So the number of sign changes is indicating that how many poles are lying on the right hand half of the S plane. So let us take another example. So it is the order of 4. So S is to power 4, 3, 2, 1, 0. Write down 2, 3, 10 in the first row, then 1, 5 and 0 in the second row. Now with the help of these two rows, okay, you determine the other coefficients of the Routh array. It is minus 7, 10. It is 6.430010. Now again, if you look towards the system, this is plus, this is plus, but this is minus, this is again plus. So again, two sign changes are there, which clearly indicate that the two poles are lying on the right hand of the S plane and the system is unstable. Okay. So we will not go to the another methods, only this now second case, a 0 only in the first column. Okay. So what happens? This is a very important question and generally asked in the examination. Okay, determine the stability of the system having characteristic equation given below. S raised to power 5 plus 2s to the power 2s cube plus 4s square plus 11s plus 10. Okay, so again you will form the Routh array. So when you form the Routh array, the first row 1, 2 and 11. Very correct. Then the second row 2, 4 and 10. That is very clear. Now you just find out the coefficient of the remaining rows. Okay, so elements of the remaining row. So 2 to the 4 minus 4. It comes out to be 0. Okay, here it, though I have written option, but it is 0 basically. Similarly, 11 to the 22 minus 10 divided by 2, you will get something like 12 divided by 2 is 6. 0. Then now when you will get 0 here, what happens? It will create a problem, because in the remaining element you have to divide everything by the 0. So divided by 0 is not permissible in our so-called mathematics. So what we will do, that we will, if now mind it, this is the case when only one element, that is the first element of any row, is becoming 0. Okay, not all the elements. So here only this is becoming 0, not all the elements. When all the element will become 0, that will be the third case. Here only the element in the first column is becoming 0. So what we will do in this method, instead of 0, we will write an symbol called option. Okay, and we will call this is a very small number, where option is a very small number, approximately to 0. Okay, so now we will solve with the help of this. So what will be the element C1? C1 will be nothing but 4e minus 12 divided by option. Okay, and the remaining element 10, 0. Here it will come D1. D1 will be how much? 6C1 minus 10e upon C1. Okay, okay. Now after obtaining these elements, now we will apply limit option tends to 0. So what will happen if I apply limit option tends to 0 in this C1? What will happen? I will get minus 12 by E. 12 by E. So E, what is option is there? Option is a very small positive number. So definitely this quantity will be a negative number. If option is a very small positive number, okay, this quantity will be a negative. So it clearly indicates that this is being positive, C1 is negative. Now look towards D1. If I will apply limit option, because C1 is already minus 12 by E, so when you will put it and apply limit option tends to 0, you will get 6. So D1 is approximately a positive number. So what you will get, this is positive, option is already positive, C1 is negative, D1 is positive 10. So there are two sign changes are there, from positive to negative and negative to positive, which clearly indicate that system is unstable. And how many roots are lying in the right hand of the S plane? 2 roots are lying in the right hand of the S plane. So if first element in any row is becoming 0, then we have to apply this method, that is assign it them as a small positive number optional, and then solve it, apply the limits, and then indicate that what sign changes are there. Now, then let us take example of this. Determine the range of param for system is unstable. Now, again, you will see when you will form the Routh array, in this case, 1 minus 1, 1 minus 1 divided by 1, so it will become 0. So whenever while it is k, it is 0. So only this is becoming a 0. So only one element is becoming 0. So what I will do, I will substitute it as epsilon, and now I will solve it. Epsilon minus k upon epsilon. So this will be my C1, and what again when I will solve this C1, it will come out to be K1. So I need not have to worry. Now I have to indicate what is the sign of the C1. So again I applied limit epsilon tends to 0. So 1 minus k upon E. So what I will find, it will find out to be minus k upon E. If it is a positive, then definitely this whole number is a negative, which clearly indicates that C1 will be a negative. So in order that system to be stable, k should be also negative. Okay, that is, so if the value of k is greater than 0, system is unstable. Okay, because it will be a positive quantity and it will make the thing negative. So in order to be system to be stable, k should be less than 0, that it should be negative, so that it will become positive, and all the elements in the first column will be positive, hence system will be stable. And therefore in order the system to be stable, okay, here the question is asking the parameter k for system is unstable. So for k greater than 0, okay, for k greater than 0, the system is unstable. Okay, so that is very clear that if k is greater than 0, system is unstable. This is the range of the, so k from 0 to infinity is the range, okay, for which the system is unstable. Okay, so this is another example. Okay, you can look towards the example. Okay, it is of order of 5. So s raised to the power 5, 4, 3, 2, 1, 0. Again, a 0 element is forming. So epsilon is there, 6 epsilon, this. You have solved this equation. Okay, find out the limit, and again you will find the limit that sign changes are there, and therefore there are two sign changes will be there, and hence the system is unstable. Okay, and two post line the right hand of the S plane. So we will not take I will directly jump to the case third, where the entire row is becoming 0. This is a very important case. Okay, so let us directly start with the question. So it is a question is there, s raised to the power 5 s. This is the correct equation. I will form the first two row. Okay, now in the first two row, when you solve it, when you form the third row, you will find that every element is becoming 0. Every element is becoming 0. Okay, so in this case, if any element is becoming 0, what will happen? That we will form an auxiliary polynomial from the row just of the row which is becoming the 0. So first we return to the row immediately above the rows of zeros and form an auxiliary polynomial using the entries in that row as coefficient. So s cube row is becoming 0. So I will just above is s raised to the power 4. So I will take its coefficient, and its coefficient will be s raised to the power 4 first. Then instead of s cube, I will take s square, because I am taking alternative element. So 6x square plus 8. So this is an auxiliary polynomial PS. Now I will differentiate this polynomial with respect to ds. So these are the method I am telling you. So when I will differentiate it, I will get 4s cube plus 12s plus 0. Okay, so finally we use the coefficient. Now whatever the coefficient of this differential are coming, 4 and 12, I will place these coefficient in the 0th row. So here I will place 4 and here I will place 12. So it will become, I can simplify it also, 1 and 3. So I will become 1 and 3, and remaining, then I will find out the remaining Routh array coefficient. So what I am finding, that all the elements in the first column are positive, hence the system is stable. So this is the case third, a very important case where all the elements are becoming 0. So what you will do, you will form an auxiliary polynomial from the coefficient of the row just above that 0th row, and then you will differentiate it with respect to s. You will get certain coefficient, you will place that coefficient in the 0th row, and then you will proceed further. You will find, if there is no sign change in the first column, you will say system is stable, otherwise system is unstable. So I think so Another numerical has been given to you, okay, where has been asked what is should be the value of the k in order the system to be stable. So again, it is very clear that 8 minus k upon 2 should be greater than 0, or k should be lie between 0 to 8 in order that the system to be stable. Okay, so this is so I'm ending here. So this completes your Routh Hurwitz criteria. Okay, we are not going for further any things. If I have any doubt, then please write in the comment box. I'm ready to share the things.